Welcome to Library Seminars, a webinar series put together by the NOAA Central Library to highlight research and ideas that reflect the mission of the National Oceanic and Atmospheric Administration. Today's presentation, Fisheries Management in a Non-Stationary World, Challenges and Opportunities, is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries. Our guest speaker, Professor Zhang from Shanghai Ocean University, will be introduced by the organizer of this series, Kristen Blackheart from NOAA Fisheries Office of Science and Technology in Seattle. But before I hand over the mic, here are just a few bits of information for our live audience members. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I will add the channel's link to the chat box very shortly. Our speaker did share his slides, so please feel free to download them from the handouts menu in the webinar control panel. And most important, we're very interested in your questions, and we encourage you to ask them throughout the seminar, even though the speaker will not address them until the very end of the presentation. All audience members are muted, so type your questions or comments in the chat box under questions located in the webinar control panel. So let's get started. Kristen, the mic is yours.
Thank you, Lisa. I came across Dr. Zhang's research when I was reviewing some recent literature on non-stationarity and decided to invite him to come and speak with us. And when I extended that initial invitation, I did not realize that there would be such a time zone difference. So we are very grateful that he has agreed to join us and share his research. Despite the considerable time zone difference, we're very appreciative. So Professor Zhang is at the Shanghai Ocean University, where he studies several areas of fishery science, including fish population dynamics, stock assessment, and fisheries management. He obtained his bachelor's and master's degrees at Ocean University of China, and then went on to study his PhD at the University of Guelph. Before taking his current position at the Ocean University in Shanghai, he was a research scientist at the Memorial University of Newfoundland. So with that, I will once again thank you for being with us and sharing your research, and I'll turn it over to you.
Thanks, Christine and Lisa. Hello, everybody. It's a great pleasure to join this webinar seminar. And today, I would like to share some ideas on non-stationarity in the context of fisheries management. So first, I would like to briefly talk through what are the traditional ways to do fisheries management. So I guess everything starts from data, right? So we first go out to collect fisheries dependent and fisheries independent data. And then the data feeds into some kind of stock assessment model. For example, surplus production models or age structured models. And then by implementing these models and estimating parameters, then we got two kinds of information. So first is some estimates of the population size, like abundance, biomass, or fishing mortality and other metrics. And the other type of information, which we often call reference points, basically like the target or limit biomass or fishing mortality we set for the stock. And by comparing the estimated population size versus the estimated reference points, then we can get the status of the stock. And then based on the stock status, then we come up with some kind of management strategies like TAC, like harvest control rules, total allowable catch, and other types of strategies. So basically, this is how we do traditional fisheries management for the past, I think, few decades. So when we do this kind of practice, there are actually some kind of strong assumptions which are equilibrium based. So these assumptions basically underpinning many aspects of this traditional fisheries management. So what are these equilibrium assumptions, and where and how these assumptions underpinning the traditional framework? So when we talk about equilibrium assumptions in stock assessment models, basically that is the first place where we place these assumptions into the framework. So for this, I would like to talk about these equilibrium assumptions from 3 levels or 3 aspects. So first is the concept. The concept, one important concept for these equilibrium assumptions is that population size eventually reaches equilibrium without fishing. So that's like a very basic assumption behind different kinds of stock assessment models. And from this very basic concept, then the next level goes to the how do we interpret this concept. So this concept then goes to be translated into the population dynamic models. So basically we consider the population vital rates are constant over time. And when it translates into the specific models, the mathematical equations, that goes to the final level, which is we assume the key parameters of the stock assessment models are constant. So here I just give 3 very common examples of how these equilibrium assumptions play out at the equation level. So the first one equation, I think most of the audience will be very familiar with, which is the surplus production model. And as we can see, the parameters R and K will be the key parameters that specify how the population will progress over time. And by assuming equilibrium dynamics, then we basically assume the R and K parameters are constant over time. So this is one simple example. Another common example is the stock recruitment model, which is the second one. And this is the Beaverton-Holt model. And we have the alpha and beta parameters, which in the traditional assessment, we usually assume they are also constant over time. And another example will be linked to the age-structured models. For example, the cohort progression models, like the third one. And in traditional practice, usually we assume the natural mortality as a key parameter is constant over time because of many difficulty to estimating that and the uncertainty surrounding that. So these 3 are just some examples of how we implicitly place the equilibrium assumptions underlying our daily practice in stock assessment. So this is and when we have these equilibrium assumptions in these stock assessment models, by having these constant parameters being estimated, then we can move on to go to the next level of calculating reference points. Probably one of the most commonly used reference point is MSY-based reference points. And if they are derived from the surplus production model, then we have the FMSY and BMSY directly linked to the R and K parameters. So this will give us very specific reference points we are trying to compare against. So then by having the estimated population abundance and this specific reference point, we can then move on to come up with, for example, the Kobe plot, which is basically compare the current population biomass or fishing mortality against the MSY-based reference point. And from this one, we can define the status of the stock, whether it's overfished or it's overfishing. And this plot is probably one of the most commonly used plot in the current stock assessment practice. So then after that, after we got the status of the stock, then we move on to the management strategies. And then because we have some specific reference points, we can have this very common like stepwise harvest control rule. The x-axis is the biomass, and y is the fishing intensity or fishing mortality. So by having this type of the harvest control rule, then that feed directly into how we define the total allowable catch or the quota for the fisheries. So basically, as we can see, the equilibrium assumptions just goes from the stock assessment model to reference point to the harvest control rules, and just goes through most of the stages of the traditional stock assessment. So here comes to the question. So we have these equilibrium assumptions, but are these equilibrium assumptions valid? So from the very top level of the concept, we may ask this question. So is that true? The population size will eventually reach equilibrium without fishing? Do we think this assumption is valid or is correct? So here is from the classical theory of ecology, basically depending on the intrinsic growth rate. And this is if we follow a logistic growth curve, then the population will reach some type of equilibrium dynamics. So whether it's a constant biomass, or it's a limited cycle with different patterns. That depends on how we define the intrinsic growth rate. And if we further increase the intrinsic growth rate, the population may go to chaotic dynamics. So which means there are some conditions on this assumption. So depending on the actual value of the intrinsic growth rate, the equilibrium may not be reached in the sense we think. So basically usually we think equilibrium state is a constant level, but in many cases it may not be that, even from a single population dynamic perspective. So some people may criticize this argument by saying, okay, so these plots are basically theoretical plots. So you control the intrinsic growth rate by allowing different unrealistic large values. So in the nature, in practice, we won't see much of the limited cycle or chaotic dynamics. So we may only see these equilibrium dynamics. So okay, so if we just try to, if we think that is correct, even though then we may have encountered another interesting situation about these equilibrium assumptions. So the next challenge for these equilibrium assumptions is the multiple equilibrium dynamics. So basically that is considered as a major conceptual change in the discipline of ecology. So basically shifting from the single equilibrium perception of the ecosystem to a multiple equilibrium dynamics. And the original work comes from Buzz Holdings' work on the resilience and stability of ecological systems, then goes on with many authors and with many different following example natural observations of the multiple equilibrium dynamics. So basically the concept is for many ecosystems, instead of have a global equilibrium, they may exhibit multiple equilibriums. A classical example is this cup and ball dynamics. And if we consider the current state of the ecosystem is represented by the ball, it can roll between different basins. So sometimes we call that attracting basins. So different multiple stable states. So in that case, the population dynamics may have more than one equilibrium state. So that will cause a big challenge to our traditional single equilibrium based assumption. So this is one big challenge. Another challenge also originates from ecology is the so-called long transient. So a long transient is a persistent dynamical regime happened during the regime shift. So this non-equilibrium dynamic may persist for very long time. and this time may be very relevant. For example, take decades of year, if it take decades, and that is relevant to our fisheries management. And if a fish population is undergoing a long transient, then the so-called equilibrium-based assumptions may not be valid or hold for these types of dynamics. So from the conceptual concept, we have different challenges on the equilibrium assumptions. Then if that further translates into the next two levels, we may further question. So all population vital rates may not be constant over time. And then if it goes to specific stock assessment models, then the key parameters of these models may not be constant. And this is where the non-stationarity kicks in our fisheries management. So here I just want to give two examples of these so-called non-stationary dynamics. The first example is the so-called non-stationary stock recruitment relationship. So basically that is reflected from this equation by allowing the key parameters alpha and or beta to change over time. And another example which have been well identified is the time varying natural mortality. So instead of assuming M is constant or simply equal to 0.2, the natural mortality rate may actually also change over time. So surrounding these two topics, I would like to give some examples, which from other study, which from my previous research. So first, I would like to focus on this non-stationary stock recruitment relationship. So what is this non-stationary stock recruitment relationship? So, well, we all know what is a stock recruitment relationship. So basically that describes the relationship between spawning stock size and the subsequent recruitment. So by introducing this non-stationarity, it means at a different time, the shape of this curve may change. So for example, at time 1, then the spawning stock size is at level B is actually producing a greater recruitment than level A. But if the shape of this curve change to a different type in time 2, then we will see, well, and when the spawning stock size is at level B, it actually have a very similar recruitment output as to the level at A. So this type of change actually will have a very strong impact on our interpretations and decisions for the management of the fisheries. So this is like the concept of this basic concept of non-stationary SR relationship. This concept was arguably first proposed by Carl Walters in 1987 in a paper describing the possibility of this phenomena. And then in around 2003, there were a field work from Randall Pittman and his colleagues on the salmon populations on the west coast of America. And basically, they use Kalman filter to allow the time varying alpha of the SR model, and then discovered the productivity of the salmon populations actually show large change over time. And then another piece of example comes from the Atlantic cod stocks, and led by Colin Minto and his colleagues. They discovered for cod populations, their productivity also tends to change over time. So build on these previous studies on research, then I move on to my work at Great Lakes during my PhD. So that work basically is trying to see if there are non-stationary SR relationships of yellow perch in Lake area, and specifically on the west basin of Lake area. So why do I care? Why do I think there are non-stationarity of SR relationship in this ecosystem? Well, because as I will introduce now, this ecosystem is quite interesting. So Lake Erie is probably one of the most well-surveyed lake among the 5 Great Lakes. And we have a very rich survey data from 1975 to 2015, which is the period I used for my PhD research. And during this time, there were 2 major events. First is the zebra mussel invasion. If people are familiar with this ecosystem, this is a very major event of invasive species in the Great Lakes. And another event is the eutrophication or re-eutrophication around 1995, 1996. So because of these 2 events occurred on the in Lake Erie, and there has been some large ecosystem change associated with these 2 events. And that basically divides the whole period into 3 periods. So first period is before the zebra mussel invasion. The second period is after invasion but before eutrophication. And the third period is after eutrophication. So basically my objective is to try to see whether the 3 periods shows different SR relationship for Lake Erie yellow perch. So what I did is basically have two models. So first is the default, which is the traditional time recur SR model with the parameters constant over time. And another model is the modified one by allowing the alpha and beta parameters to change over time, specifically change among the 3 periods. And then after fitting the data using Bayesian methods, and the DIC of the 2 models are compared to see which model is preferred. And basically the results indicate the second model, the PRM model, has a much lower DIC, which is preferred. And then I went on to see how the result from the second model different from the first model. So basically, the result can be interpreted into a change of the SR relationship. If we look at the western basin of this lake area, so as we can see from period 1, which is a red curve, which we will see sometimes when we interpret it's more productive. And then after the zebra mussel invasion, this curve is crest to the green line here. And then after the event of eutrophication, it actually goes back a bit into this purple line. So this is one result from this work. And there are other results from the central and the eastern basin, which I will not talk in detail today. But if you are interested, you can go to the paper we published in ICIS journal to see more details of this research. But basically, the point is, from this case study of yellow perch, we discovered there are non-stationarity did exist in this ecosystem. And then I move on to another example of Newfoundland cod. So that is, so here is where, so it's basically in NAFO region 3NO, which is 1,000 grad bag of Newfoundland region. And I think most people will be very familiar with the major class of cod fishery in the Northwest Atlantic. There's still debates on the mechanism causing these collapse, but I guess it's a mixture of overfishing and climate change. So here, for this work, we are trying to discover whether non-stationary SR relationship exists for the cod stock in 3NO, which is 1,000 grad bag. So for this work was led by Xiaozhuo Tang, which is my master student at Memorial University, and she actually designed a different method to test for this kind of non-stationarity. And this new method is called hidden Markov model. So basically, instead of allowing the alpha and beta parameters to vary over time following random walk or autocorrelation, for this new model, we allow the alpha and the beta parameter to change following a hidden Markov process. So there is a more like a discrete process. By doing this, we basically assume, so first we have to specify how many regimes there and then estimate the probability of how the stock is shifting between different regimes. So there are many technical details of this model which you can find, which I will not talk too much math today. So if you are interested, you can go to this paper also on ICIS journal. But the main idea is first we use a simulation test to see whether this new method is able to detect a regime shift. So basically we have three scenarios. The first is no regime shift, second one is 2 regimes, and third one is 3 regimes. And by doing this simulation testing, basically we verified this new developed hidden Markov model is able to accurately detect and estimate different regimes of the SR relationship. And then we apply this model to the actually population of the 3 annual cod. And we fit the data to 3 models. The first model has only 1 regime, no regime shift. Second one has assuming 2 regimes. Third one assuming 3 regimes. And the models were compared following the AICC criteria. And then the second one stand out, and we went on to estimate the parameters, and then we see a clear regime shift of the SR relationship for this stock. So basically, this gives a second example of whether non-stationary SR relationship exists in the nature. So that's 2 examples of non-stationary SR relationship. Then so now I would like to talk another example of the time-varying natural mortality. So whether natural mortality change over time. So this involves 2 works we have done on the Atlantic cod of Newfoundland and the Labrador. The first is purely statistic. It's basically using the juvenile survey data to estimate the spatial temporal variation of the juvenile mortality. And the interesting result is we see some strong variations of the juvenile natural mortality. So by assuming the fishing mortality is minor or negligible for juvenile cod, so basically the whole total mortality are caused by a variation of natural mortality. And we discovered this very interesting cyclic dynamics of natural mortality. And then another work done by Paul Regular and the others was focusing on some more mechanistic explanations of the time-varying natural mortality for northern cod. So basically, we used some starvation index derived from the body condition of the cod to estimate the natural mortality. And interestingly, for the younger cod or juvenile cod, we also see some cyclic patterns of the estimated natural mortality, which kind of match what we got from a totally different data source and methodology. And by taking these 2 studies together, I think we would be more confident to see, well, the natural mortality will change or could be changing over time for this specific stock. So this is one example of time-varying natural mortality we did for the cod stock. Obviously, there are also many other papers on time-varying natural mortality, and I think we even have a CAPM seminar, a workshop held like 1 or 2 years ago on this topic. So I think so this is basically giving some some illustrations on how we have explored the possibilities of non-stationarity in the stocks. So the next question will be, why are there non-stationary population dynamics? So why do they exist? So commonly we will consider there are two major sources. The first obviously is climate change, whether it's ocean warming, acidification, sea level rise, or polar rise melting and others. And a second aspect is the human activities, pollution, fishing, and other activities. So what strikes me is, although we have discovered many patterns of non-stationarity, but a very strong causal link to these potential mechanisms are still rare in the empirical cases. So which may be a very important research direction in the future. So here we have talked about for now we have talked about the traditional fisheries management and how equilibrium assumptions play out in the traditional framework, and why these equilibrium assumptions may be invalid, and also gave some examples of non-stationarity in empirical studies. So here, from now, I think hopefully you may be convinced non-stationarity is real. It's not like a mystery. And so next stage, natural question will be, well, if there are non-stationary population dynamics, and does it matter? What that means to fisheries management? So for this, I would like to today I would like to talk from two aspects. The first one focusing on stock assessment models, and second focusing on reference points. So from the stock assessment models, I would like to refer to a very interesting concept, so the trade-off. I think for many fisheries scientists, from the beginning of our training, we have a common sense or some belief, like if we have a longer time series of data, and then we will have a more accurate stock assessment estimates. So basically that is which I will call the longer the better. So if we look at this figure here, the x-axis is the length of time series data, and the y-axis is estimation error due to these measurement errors. So this basically, as we have a longer and longer time series, the estimation error tends to be smaller. So the longer the better. Why do we have this? Well, probably linked to our basic understanding of the statistics, the law of the large numbers. So if we have, assuming we have a larger sample size, we can more accurately estimate the true parameter value. So that's basically underlying this whole concept to some extent, although we all know time series data points are not independent. But I think that is a general belief. So here comes to a next concept, which I term as the shorter the better. So why this kicks in? Well, this basically links to what we have described as a non-stationary dynamics. So assuming, for example, an ecosystem experienced a regime shift on a certain point, then the data before that regime shift may not be relevant to our current stock status. So if we use a longer time series data, which including these irrelevant information, then that may make our estimations worse. So by using a more recent time series data, we actually may be able to get a more accurate estimation. So this gives to the concept of the shorter the better. And in reality, actually, the two processes occur simultaneously. So which means the two things should be taken together, and that could give us a trade-off. So basically, there might be some sweet spot along the length of time series data, which can give us a minimum estimation error. So this is the so-called trade-off. So this is more like theoretical practice, theoretical argument, or thought experiment. So is this true in stock assessment? So that basically is the motivation of this paper we did for this question. So what we did is we just choose a very simple and common stock assessment model, and using a simulation framework to test whether that trade-off is true. So basically, this simulation comprises 3 components. So the operating model basically has the surplus production model, but assuming the intrinsic growth rate R change over time as a subscript T. And for the assessment model, which is a traditional default surplus production model with constant R and K parameters. And then there is an evaluation model with different, so we have the EEW, which is the estimation error over the whole time series, and also the estimation EEL, which is the estimation error for the last data of last year or the most current year. So this is basically the simulation framework. And by using that, we first test the idea of the longer the better. So the longer the better, in this scenario, we assume the intrinsic growth rate is constant over time. So there is no non-stationarity. So in this case, basically, as expected, we have this, from this the middle panels here. The x-axis is the length of time series. The y-axis is the 2 metrics of performance, the whole estimation error across the whole time series, or estimation error from the last year. And we can see there is, as expected, it follows the longer the better. So as we have a longer time series, we have a more accurate estimation of the population size. So this confirms our first argument. The second argument, which we take the scenario of a regime shift, which is we assume the intrinsic growth rate has a regime shift around the simulation year 20. So we have 2 regimes, and by implementing the simulation, then we discovered the estimation error and the length of time series exhibit more like a positive correlation. Well, which means when we have a longer time series, length of time series data, the estimation error actually increase. So this matches our argument of the shorter the better. So the next stage, which we generalize to a more common situation, basically we allowing the intrinsic growth rate to just vary following some AR1 process. And we have a strong autocorrelation versus weak autocorrelation. And then we set different levels of measurement error. And then by plotting the same relationship, we can see for different combinations, we see different patterns. Sometimes it's the longer the better, sometimes it's the shorter the better. So basically, there are some trade-off between measurement error and process error. And this further confirms this trade-off actually exists. So how to resolve this trade-off? So why it occurred? So the obvious reason it occurs is because model misses specification, because operating model and assessment model have different assumptions. So by resolving that is actually resolving this model misspecification by using the same operating model and assessment model for this simulation. And then as anticipated, by doing that, this trade-off is resolved. So by matching the operating model and assessment model, everything returns to the longer the better scenario. So we can comfortably using longer time series data for this practice. Can you confirm if you can hear me or?
Yes, I can hear you.
Okay, so it might be a mismessage or incorrect message. Yeah. Okay.
Yeah, you're good.
Okay, so from this whole simulation practice, that actually goes back to a more general concept or a phenomena. So in our traditional stock assessment practice, we tend to think, well, data is fixed. So basically, we are balancing the model complexity with the estimation accuracy. So this is what we are most familiar with. We try to adjust the number of parameters, the complexity of the stock assessment model to match the data, and to a certain level when the estimation accuracy is the highest. So that is the traditional way we think about it. And then from this paper, we actually perceive the same problem from a different perspective, which we are assuming, well, if the model is fixed, then there actually is a trade-off between data complexity and estimation accuracy. So by data complexity means how complex the natural process is. So why do we have that trade-off is because when we have a longer time series data, the natural dynamics is more like the natural population is more likely to experience a more complex dynamics, like regime shift and the stronger effects from the climate change and other factors. So that we interpret as a data complexity. But the solution for the two situations are actually the same, which is to match the data with model. So match the model structure to make sure the model structure is realistic enough to represent the data we input to the model. So this is basically the main idea from this whole process of that, the trade-off. So the final one I would like to talk about what this non-stationarity implies for reference points. Well, so I guess the first question is, what are reference points? So what are reference points? Are basically some quantitative metrics, like quantify a certain status of fishery. So by, for example, some commonly used reference points are basically associated with some different reference status. For example, B0 is a reference point associated with the unfished status, and B-lame is from the definition comes from SR relationship, and MSY is linked to the status of MSY, and Fmax or yield per recruit depends on the post-recruitment survival process. So this is basically the how we usually define a reference point. So for the equilibrium assumptions, underlying reference points are basically linked to our assumptions of the vital rates or key parameters of the stock assessment models. Because these key parameters are constant, then we have a static or fixed reference points. For example, the BMSY from the surplus production model is basically half of K, which is the carrying capacity parameter. So what about non-stationarity? So if we have non-stationary population dynamics, that means the key parameters are changing over time. And from a broader sense, basically there are, when we calculate the reference points, the historical data may not be relevant to inform the current level of for the reference points. And the second aspect is the future population dynamics are uncertain. So how the key parameters will change in the future. That will be two major challenges when we try to define reference points. So the historical data may not be relevant is basically reflected from several literatures. This is an example for Atlantic cod, which basically from the previous period, from high average and low productivity period, the key reference points like Fmax, Fmsy are quite different among different periods, which means if there are some regime shift, that has a very straightforward direct impact on reference points. And then sometimes people will say, okay, if there is a reference point, we may try to using only the most relevant length of time series. Sometimes we call that the prevailing condition for the current assessment. The problem is, what is the most prevailing condition, and what is the most relevant time series? And this choice actually is very important, because there was another work done by Michael and others showing the limit biomass limit reference points are actually very sensitive to how long the time series used to calculate them. So how another way to try to deal with the time varying parameters in the past is by accounting for these parameters directly. So recent work by Jeremy and Colleen basically using the time varying SR relationship, using the time varying parameters to calculate the most recent reference point. So I just want to point to one example here, which is FMSY. So by following the time varying alpha parameter from the SR relationship, the FMSY can be calculated as a dynamic reference point, which obviously change over time, as opposed to the constant one, which assumes assumes stationary dynamics. So this is another way of dealing with the historical change. So I think the bigger challenge might be in the future. So how, if there are non-stationarity in the past, we probably anticipate that will continue in the future. But how do we project that into future? Because as we know, for many reference points, we have to project. For example, MSY, it is defined as the long-term dynamics. So how do we do that? Well, broadly speaking, I think there are four categories. Well, the first one is simply ignore the variation, well, assuming it's not changing over in the future. Well, sounds weird, but actually this is the most commonly used way in the current assessment world. Many stocks basically, when it goes to projection, actually ignores potential variation of the key parameters in the future. So a second way could be, well, just resemble the historical pattern in a very vague way. So for example, if historical pattern follows some type of autocorrelation, then future they may continue this type of autocorrelation. The third one is including environmental covariates by, for example, water temperature and other driving parameters could be incorporated into the reference point. And the fourth one could be constrained by the ecosystem dynamics. For example, if there are regime shifts, then maybe this whole regime could be carried on for the future, at least the near future, which could be used to constrain the future dynamics. So so I'll leave the first one to, that's a common practice, not much to talk about. I will start from the second one, the resemble historical pattern. So how do we do that? So for this one, we basically did a research for this by calculating MSY-based reference points from, the non-stationary SR relationship by assuming different variation patterns. As we can see, whether it's constant or assuming some process error, the dynamics are pretty different to the historical one. But we have some different methods by allowing autocorrelation of the SR key parameters. Then we see a more, similar patterns in the future as to the past. So the take-home message is, by using different methods, we actually have calculated the different relationship between fishing mortality and yield, which gives us very different reference points. For example, FMSY and BMSY. So this pattern matters. Whether you project with autocorrelation or without autocorrelation, that will give us a different value of the reference points That is this for this topic. And then the next one is including environmental covariates. And I mean, this one has been discussed over years, but still there are two big challenges. Environmental drivers are difficult to identify for most stocks and ecosystems. And even though there are some correlation identified, these effects may change over time, may be different in the future. So I see the time is very tight, so I will just go briefly to this example of non-stationary environmental effects, which we did for the American Place and the yellowtail in the brown bag. The take-home message is actually there are some non-linear and discrete dynamics between water temperature and the distribution and the population abundance of the two stocks. So which further collaborate the second point. Environmental effects on population dynamics may change over time, may not be that straightforward. So the last point will be, sometimes we can, if we can use some broad scale ecosystem dynamics to inform the future dynamics. Well, this is most applicable when non-stationarity are associated with ecosystem regime shift, and also conditioned on some very challenging points, which is, well, ecosystem regimes could be accurately and timely identified. This is a big challenge. And if future regime shifts can be predicted, either from early warning signals or other methods, these are some challenges by adopting this research. So basically, for now, I think there hasn't been a very effective and well widely acknowledged method to do this, to deal with reference points yet. So we had a workshop on dynamic reference points like back in 2021, and even from the very basic definition of what is dynamic reference points, we have very diverse responses. So I think this is a very long way to go in the future, and this is also a very important thing we should consider in our practice. So more work are being working now, and hopefully we'll see more results in the future. So basically, then the final slide with a take-home message. Well, first is, I guess, hopefully many of you might agree, non-stationarity challenges these equilibrium assumptions of traditional management. And for both stock assessment models and the reference points, we need to account for these time-varying vital rates if they exist. And the third one, I think, is more conceptual. Non-stationarity, may need to be considered as a norm instead of exception, because, to be frank, everything is non-stationary if you look close enough and long enough. And obviously, continued research on this topic is needed, especially on the ecological mechanisms. So with that, I would like to end the presentation and acknowledge all the universities, institutions, and funding agencies supporting all this work along the way. And I would like to take any questions if there are any. Thanks.
Thank you so much, Professor Zhang. We do have some time. We have about 6 minutes for questions, so I encourage audience members to type them into the questions chat box in the control panel, and I will read them to our speaker. But before I do that, I do see there's one question. I want to remind people that Professor Zhang has shared his slides with us, so please feel free to download them from the handouts menu now before we end the session. And one last thing, I'm about to hit the send button, and you will see that we have a link there to the NOAA Central Library YouTube channel, specifically the this series playlist. And I encourage you to, in a couple of hours, to share the link to Professor Zhang's presentation with anyone who might be interested. So let me look at this question really quick. All right, so Professor Zhang, this person says, great talk. I'm wondering if you have considered the situation where the data do not accurately capture the dynamism in the system. For example, hyperstability or fish have left the survey area. Do you feel the measurement error variable was sufficient for this question?
Well, that's a good question, and that actually goes to my slide on the trade-off between process versus measurement of observation errors. So if for a fishery or stock, the measurement error is too large and large enough to obscure or cover the process error, I think this non-stationarity will be very difficult to identify. And to do this type of research, I think we should have a certain fairly degree of confidence in a situation when we believe the data has a fairly degree of certainty or accuracy. Then I think this question could be better answered. So basically, it's basically a trade-off between process and measurement error. But in some ecosystem, for example, there are very strong ecosystem regime shift, which means the process error is likely to be very large. And sometimes that may be much larger than the observation error or measurement error. In that case, this non-stationarity could be very well be identified. Yeah, thanks.
Thank you for your response. I'm going to wait to see if we get any more questions. And while I do that, I also want to mention that the professor mentioned many wonderful articles in the presentation. And of course, this is a library presentation. So if you are interested in accessing any of those articles, please contact us at the library.reference@noaa.gov. Okay, we have one other question here. This question asks, is there a distinction between non-stationary and autocorrelated variability, for example, with higher autocorrelation levels? I thought non-stationary was different than just variability.
Yeah, good question. So that's also one thing I have been thinking many times. So non-stationarity, in my view, is different to time varying, because I would consider non-stationarity as a more like a directional or systematic change rather than random fluctuations, including some very autocorrelation with very weak autocorrelation coefficient. So in that term, I would think non-stationarity is well, I wouldn't say excluding autocorrelation, but should be have the feature of directionality or systematic change. Thanks.
Thank you. We do have another question. This question asks, have you identified any tools to identify ecosystem regime shifts?
Well, there is for ecosystem regime shift, I guess, depending on the data you have, if you only have the data from a single population, in this presentation, we actually have a paper on a hidden Markov SR model, the Beaverton-Holt model, which is one method to identify a potential regime shift in the past. And this hidden Markov method actually can be integrated with different types of models. In addition to to SR model, it can also goes to surplus production model. And if there are some ecosystem models, this hidden Markov method could also be integrated to that types of models. So I think and this is only one tool, and I think there are many other tools like like smooth detection method. And so I think there are very rich literature on if you search on ecosystem regime shift, I think there are many statistical tools available there to do that in a more broad way. Even some R package there is currently available. Yeah, thanks.
Thank you. I believe that's our last question for today. If anyone is interested in contacting the professor, he has provided his email, so please write it down and feel free to contact him. Thank you again for sharing your work with us today, especially coordinating times with Shanghai and Seattle and everywhere in the world, Professor Zhang. And also to Kristen, thank you for organizing the National Stock Assessment Science Seminar Series so we can pull together all of this wonderful information. I hope everyone will join NOAA Central Library again for a National Stock Assessment Science Seminar webinar. They're hosted every month, the first Thursday of the month at 3 p.m. Eastern Standard Time. So enjoy the rest of your day, everyone, and have a wonderful month until we see each other again. Bye-bye.
Thanks. Bye-bye.